the MIT Integration Bee 2022 Qualifiers Round 1, Problems 1 through 10. We're going to go through an integral obstacle course today. At any time during the video, please feel free to pause the video and try the integral yourself. Here we go. Number 1, the integral of 1 over 1 minus e to the negative 2022x power dx. We're going to begin here by multiplying the integrand by something that looks like a conjugate here. 1 plus e to the negative 2022x power on top and bottom. That's going to give us a binomial on top of 1 plus e to the negative 2022x, and on the bottom, 1 minus e to the negative 44x. Then we're going to factor out e to the negative 22x on top and e to the negative 44x on the bottom, simplifying the binomials. And we can then simplify those two constants that we pulled out in front, get e to the 2022x multiplied by e to the 2022x plus 1 over e to the 44x minus 1. So now we can rewrite our integral. E to the 2022x plus 1 over e 44x minus 1 times e to the 2022x dx. And with a little substitution by u equal to e to the 2022x, we're going to get du to be equal to 2022x e raised to the 2022x dx. So playing around with the substitution here, we can get a substitution for e to the 2022x dx in terms of du. And the integral simplifies. And we can also do a little division here and write the integral as 1 over 2022, the integral du over u minus 1, which is the integral of the natural log, that's going to equal the natural log of u minus 1 plus c. So I is equal to 1 over 2022, the natural log of the absolute value of e to the 2022x minus 1 plus c. Question number 1 done. Next, question number 2, the integral of tan cubed of 1 plus natural log x over x dx. So we're going to start with making a substitution here of u is equal to 1 plus natural log of x and differentiating both sides of that. Then we're going to rewrite our integral in terms of u. We'll get the tan cubed of u du. It simplifies nicely. We'll split the cube up into tan squared times tan, and we'll use a trigonometric identity for tan squared, which is secant squared minus 1. We'll then distribute that tangent into that binomial, and we'll get two integrals. Now, that first integral of tan u secant squared u, we're going to make a substitution of w equal to tan u, and dw will equal to secant squared u, so this will work out nicely. So that first integral will become the integral of w dw. And we'll just write out the second integral there. Now the integral of w dw is w squared over 2, so that'll be the tan squared u over 2. Now, we're going to rewrite that second integral of tan as sine u over cosine u, and then we can make another substitution. We'll let z equal to the cosine of u, and differentiating z, we'll get dz, and then switching signs to the negative, we'll get negative dz is equal to the sine of u du. And with some substitution, this is going to work out to be a nice integral that's going to work out to a natural log. Alright, so now we can put our integral together. Tan squared of u over 2 plus the natural log of cosine u plus c. And back substituting the value for u as 1 plus natural log of x, we get our final answer here. I is equal to tan squared of 1 plus natural log over 2 plus the natural log of cosine 1 plus natural log all plus c. All right. Leveling up. Question number 3. All right, so we have 1 over a quadratic here. Let's call this integral again I. And what I'm going to do is first I'll probably rearrange the denominator there. So I like to write it as x squared minus 2x plus 2. Now, you can factor this or try to factor it, but the roots here are complex, so the factors will look something like this: x minus 1 minus I and x minus 1 plus I. So we'll be able to rewrite the denominator of that by multiplying those two factors out and rewriting this as 1 over x minus 1 squared plus 1 in our denominator. And then we'll make a u substitution of x minus 1, du will equal dx. And therefore our integral is 1 over u squared plus 1, which evaluates to the arctangent of u, which here is the arctangent of x minus 1 plus c. Integral 3, done. Integral number 4. From negative 1 to 0, we're going to pull that constant of 15,165 over 2 outside that integral with an integrand of x radical 1 plus x dx. We're going to make a trigonometric substitution of x equals tan squared of theta, motivated by that radical in the integrand, and differentiating x, we get 2 tan secant squared d theta. So I is now that constant times the integral of tan squared theta secant theta multiplied by 2 tan theta secant squared theta d theta. So we see a lot of things that we can group together. We'll pull that constant out, pull all the constants out there, and then we can group tan times secant cubed d theta. All right here. So now we're going to rewrite this integral as the constant, which we actually forgot to pull out the constant of 2 there, so I'll do that in a moment. So of tan secant squared times tan secant d theta. So splitting the cube up. All right. So those two canceled from before. So now we have 15,165 times the integral of tan squared secant squared multiplied by tan secant d theta. And the reason that we're doing this is because now we can make another substitution here. So one of the things that we're going to do first is make a tan squared substitution with the secant squared minus 1. And then we'll distribute that secant squared into that binomial. And we'll get secant to the 4th minus secant squared, and then we'll have the tan secant d theta on the end. If we make now a substitution of w equals secant theta, differentiating that will give us tan theta secant theta d theta, which is what we want. And now we're going to now substitute into that integral. I becomes 15,165, the integral of w to the 4th minus w squared dw. And so we know what those integrals evaluate to: w to the 5th over 5 minus w to the 3rd over 3, plus some constant of integration, but later on we're going to substitute those values of limits of integration, so there won't really be a constant needed there. So we have this constant. We're going to replace w with secant theta, and in order to replace secant theta with something, we have to remember that tangent of theta is the square root of x. And so setting up a right triangle for that, we can get secant theta is the square root of x plus 1. And so now we can write this as 15,165, the square root of 1 plus x to the 5th over 5 minus the square root of 1 plus x cubed over 3, evaluated from negative 1 to 0. And when we do all that evaluation, we get negative 2022. Number 5. The integral from 0 to 1 of x minus 3 to the x, quantity squared dx. So this one's going to be an interesting one. We're going to expand out that binomial squared, and we'll get the integral of x squared minus 2x 3 to the x plus 3 to the 2x power dx. And by linearity of integrals, we can separate that into 3 separate integrals and evaluate them separately. The first one, a straightforward integral of x squared, becomes x cubed over 3, and that's going to be evaluated from 0 to 1, which is going to give us 1/3. pulling a constant of 2 out of that second integral, and we'll work on that one next, the integral of x 3 to the x from 0 to 1. So we're going to do this one by integration by parts. We'll let u equal x and dv equal 3 to the x dx. This will give us a v of 3 to the x over log 3. And the integration by parts formula is uv minus the integral of v du. Okay, so writing things out, u times v would be x times 3 to the x over log 3, minus the integral of v du, the integral of 3 to the x over log 3 dx. This gives us x 3 to the x over log 3 and minus 3 to the x over log squared of 3. Okay, so it's going to be evaluated from 0 to 1. So first evaluating at 1 minus what we get when we evaluate at 0 works out to be 3 over log 3 minus 2 over log 3 squared. So our integral is 1/3 minus 2 times that quantity we just found, and then plus the last integral there from 0 to 1 of 3 to the 2x. So that's going to give us 1/3 minus 6 over log 3 plus 4 over log 3 squared plus the integral from 0 to 1 of 3 to the 2x. Now 3 to the 2x, we're just going to make a quick substitution there. We're going to let w equal 2x. Differentiating, we'll bring that 1/2 over the other side. 1/2 dw equals dx. And when we go through a little quick side calculation there, limits of integration go from 0 to 1 now to 0 to 2. And this is going to evaluate to 4 over log 3. All right, so we're going to put that together with the other negative 6 log 3, and that's going to give us a final integral of 1/3 minus 2 over log 3 plus 4 over log 3 squared. On to number 6. We're more than halfway there. The integral of x to the 12th over x squared plus 1, and that over x squared plus 1 is just begging for an arctangent somewhere. So we're going to do a little long division on this rational expression, and that's going to give us a nice long polynomial as a quotient plus a remainder over the divisor. And what you know, the remainder is going to be 1 over that divisor of x squared plus 1. So this is going to integrate nicely. So we'll replace that rational expression with our quotient plus the remainder over the divisor, a nice polynomial that'll be easy to integrate. And then 1 over x squared plus 1 will be nice to integrate as well. That's the arctangent. So this evaluates finally as x to the 11th over 11 minus x to the 9th over 9 plus x to the 7th over 7 minus x to the 5th over 5 plus x to the 3rd over 3 minus x plus the arctangent of x plus c. Long division, long explanation. On to number 7. The integral of x squared over x minus 1 over times x squared plus x plus 1. And that bottom right there just begs us to multiply that together. So we observe that x minus 1 multiplied with x squared plus x plus 1 is going to be x cubed minus 1. So we'll substitute that back in there. And now we're going to make a substitution. U is equal to x cubed minus 1. We'll differentiate to find du, and we notice that x squared dx is 1/3 du, so we get an integral that evaluates to another natural log. 1/3 times the natural log of x cubed minus 1 plus c. Number 7 was a breeze. We're almost there. On to number 8. The integral of sine of 2x over 1 plus 2 sine squared x dx. We're going to observe that the cosine of 2x is 1 minus 2 sine squared x, and so we can use this to rewrite our denominator in terms of cosine of 2x. So 1 plus 2 sine squared x would give us 2 minus cosine 2x. So now we have the integral of sine of 2x over 2 minus cosine 2x dx. Now we're going to differentiate that. U is equal to 2 minus cosine of 2x. Let's fix that. And we're going to differentiate that. That's going to give us 2 sine of 2x dx, which is in our numerator. And so now, substituting in with our u substitution, we get the integral of 1/2 of du over u, another natural log substitution. They must have really liked natural log problems this year. So the integral becomes 1/2 the natural log of 2 minus cosine 2x plus c. Integral number 8 defeated. Integral number 9 is the integral from 0 to 1 of 2x minus 1 multiplied by this, what looks to be a rational expression but has, well, radicals all throughout it. So it begs us to rationalize its denominator. So that's what we're going to do here. We're going to rationalize its denominator by multiplying both the top and bottom by the denominator's conjugate. X, radical x plus square root of 1 minus x. So that's going to give us x plus radical 1 minus x quantity squared all over, wouldn't you know it, 2x minus 1. So those 2x minus 1's in the integrand will nicely cancel out. So that leaves us with the integral from 0 to 1 of the quantity radical x plus radical 1 minus x squared. And as we did in an earlier integral, we're going to expand that integrand out by multiplying it out, by squaring it out. And that's going to give us an integrand that looks like 1 plus 2 square root of x times square root of 1 minus x. And we can split that integral by linearity. That first integral will evaluate to 1. So we get 1 plus 2 times the integral from 0 to 1 of radical x times radical 1 minus x dx. And that screams for another trigonometric substitution. Here we'll use x equals sine squared theta. We'll call that integral curly I. Curly I is the integral now from 0 to, it'll become pi over 2 is the new limit of integration. And the two radicals will cancel to sine and cosine now, and dx will become 2 sine theta cosine theta, and so we see a pattern here. So we get 0 to pi over 2 of 2 times sine squared theta cosine squared d theta. So if we multiply this integral by 2, we can pull another factor of 2 in there and write this as 2 cos theta sine theta cos theta quantity squared. And that is the formula for the sine of 2 theta. So we have sine squared of 2 theta in our integrand now. Let's make another substitution. Phi is equal to 2 theta. And we can evaluate this integral now as the integral from 0 to now pi, well, 1/2 the integral from 0 to pi of sine squared phi d phi. Sine squared phi can be written as 1 minus cos 2 phi over 2, and that'll make the integral there a little bit easier to evaluate rather than trying to work out the square. Just working out the details and using some linearity. The integral 2 times curly I will evaluate to, well, that second part there will work out to evaluate to 0, drop out, and that first part of the integral there will just evaluate to pi over 4. So 2 curly I is pi over 4. Let's put that together with the original integral I, so we'll have I is equal to 1 plus pi over 4. And there it is, integral number 9. Now if you need to see integral number 10, you'll have to check out my video that's entitled I Got Lucky, where I cover this integral and how it's done. Game on! I hope you liked this video. Please like, subscribe, and hit that notification bell for more videos. Stay tuned.